A particle to a hair is the same as a grain of sand to all of Earth. We use billions of particles, and like this we have more and more probabilities of collisions.
The HiLumi-LHC project wants to increase the data volume by factor 10. In order to get this additional aperture, we needed to develop new superconducting materials, new magnet technologies.
We will have particles running at much more energy and much more luminosity. It might give us more precision to generate new results that might give us new hints of the origins of the universe.
I am here at CERN to speak to several experts on the future of the Large Hadron Collider, the HiLumi project.
So the Large Hadron Collider is a collider that mainly is accelerating protons and doing proton-to-proton collisions. It's a 27 kilometer circumference underneath the Swiss and French border, and we accelerate two beams that are collided in the accelerators. It has plenty of magnets in order to keep the beams in orbit, and then they collide into interaction regions of the experiments. And we are studying more the elementary particles, so we are looking at the building elements of the universe.
Can you tell us how you get the particles to go to almost the speed of light?
Exactly. So it is very important. At the entry of the LHC, the elements are already very close to the speed of light. We accelerate them even more, but at some point we reach the 99.999999% of the speed of light. We cannot accelerate them anymore, then they will become more and more massive, and they will reach around 7 TeV to have a head-to-head collisions of around 14 TeV, 14 TeV. So TeV meaning a million of an electron volt. So they are quite massive in the beginning, and to be able to accelerate, we need the RF, so the radio frequencies cavities. These are superconducting cavities. We have 8 per beam, generating around 16 megavolt, so 16 million volt in order to accelerate. And the particles pass around 10 million times in this accelerator to be able to be ramped up from the 450 GeV at the entry level to the 7 TeV level before collisions.
One of the LHC's main goals was to find the Higgs boson, the particle responsible for the mass of all the other particles. That was achieved in 2012, but even before that great result, the project team was thinking decades ahead.
When we found the Higgs, in the end, the question was how can we sustain the performance of the LHC for a very long time period? Already at 99, 2000, the first ideas for how to upgrade the performance of the machine were considered. And one should say ballpark figure, the HiLumi is a 1 billion Swiss francs project, ballpark figure. And then if you count the time, we started conceptually 2011, got approved 2016, and we will start operation in 2030. So it's a very long time.
Can you tell us a little bit what are the steps that you're taking here to construct the next big upgrade and how it's going to change the LHC?
So the LHC, basically, we have the RF cavities that are accelerating, and then we have the superconducting magnets to keep them in orbit. Imagine we have a satellite. If we don't have the gravity, it will not orbit around Earth. In the same way, we need a superconducting magnet to generate a Lorentz force in order to keep these protons or any particles in orbit. At some point, we need to collide them to generate physics. So that's why we have, before the experiments, a final focusing. We need to focus the beams and to head the collisions. A particle to a hair is the same as a grain of sand to all of Earth. In order to collide them, we work with probabilities. So basically, we need to increase the number. We use billions of particles inside a bunch, and like this, we have more and more probabilities of collisions. Collisions meaning what we call luminosity. So luminosity is the number of collisions per second. Now, LHC has a defined luminosity pattern because of the final focusing of the quadruples before the interaction regions, before the experiments. In HiLumi, we are using much more powerful magnets, using fields that are 1.5 times the fields in the LHC in order to focus them more and have more and more probabilities of these collisions. This ultimately will lead to more proton-to-proton collisions, making more luminosity, making more science, and this is worldwide. All the physicists in the world will take advantage of this. So the LHC has attained its main mission, which is discovering the Higgs boson. So now in the HiLumi, what we are looking at is having much more collisions, much more luminosity, much more data for the physics community worldwide, and to be able to generate more and more Higgs boson, and to be able to have more precise measurements on this very important particle to our understanding of the universe. Trying to as well learn as much as we can, mainly to be able to understand dark matter, dark energy, and the vast majority of the universe that we don't understand around us.
There are 4 experiments in the LHC. ATLAS and CMS are multi-purpose, looking at all the particles that are produced in collisions. ALICE focuses on the collisions of heavy ions, and LHCb is trying to work out why the universe is made of matter and not antimatter. There are 4 experiments around the Large Hadron Collider today: ATLAS, CMS, ALICE, and LHCb. The upgrade of HiLumi will impact just the multi-purpose one?
No, all 4 of them. And I think one should there probably also underline that HiLumi is one part of the general upgrade. There was in the long shutdown 2 period, so 2018-ish, the LHC injector upgrade project. It's a separate project which refurbished and improved the performance of all the injector complex of the LHC. Also planning for a major upgrade in long shot 4. The one after we run the HiLumi for a while, and that is still being discussed and needs to be fully approved, but I think it's quite certain it will come to. And therefore all 4 experiments will be upgraded and benefit from HiLumi.
The LHCb detector that we had a chance to visit will need upgrading to deal with the increased number of collisions.
The new detector will start to be replaced by 2030. And what will happen is that also in the LHC, we will have particles running at much more energy and much more luminosity. Most of the detectors will add different layers, more sensitivity, and also a measure of time of the particles, which is something that we do not currently have in this detector. Essentially, with the use of time, we will be able to rebuild exactly which were the primary vertex of the collision, since we will have much more than the ones we are having here. It might give us more precision to generate new results that might, of course, give us new hints of the origins of the universe.
So we're here in the underground structures for the High Luminosity LHC. At each of the general purpose experiments, ATLAS and CMS, we construct about 600-700 meters of new underground areas, about 100 meters underground and about 20 meters away from the LHC tunnel, where we plan to install all the new equipment required for running the new components of High Luminosity LHC. In the machine itself, we take away also about 600 meters at each of the main experiments. Large number of magnets have to be replaced with more performance and more state-of-the-art equipment. And the underground galleries have 2 purposes here. One is to protect the equipment from radiation that emerges from the operation of the machine, and to give more easily access to the equipment as we run the machine, because here people will have access even if the machine is running, but into the tunnel where the magnets are, you cannot go when the machine is running. The HiLumi-LHC project, with respect to the existing LHC, wants to increase the data volume by factor 10, ballpark figure. So the way you have to envisage that is that the protons in the machine, they collide inside the detector. There they get transformed to secondary particles, which in the end is just radiation showers that go into the detector. And most of these particles get all absorbed in the detector. Some of them, however, they leak out of the detector region and they go into the machine part, where they have to be absorbed by the first magnetic elements in the tunnel. So these magnets in the LHC are continuously, when you run the machine, exposed to radiation, hadronic showers, and that will in the end impact the aging of this equipment, and it will in the end die and no longer be operational. So the challenge for the HiLumi-LHC is to produce equipment which is compatible with 10 times more data. 10 times more data means 10 times more radiation, and yet we don't want to exchange the equipment every other year just to make it run. So these magnets have to be much more radiation hard for the HiLumi area, and the way we achieve that in HiLumi is we make the apertures bigger, and then we put active shielding, to tungsten blocks, inside the magnets between the coils, which are sensitive to radiation, and the beam. And they absorb the bulk of the radiation. In order to get this additional aperture, we needed to develop new superconducting materials, like niobium-3 tin, new magnet technologies, and make this a real thing available for accelerator physics. In difference to the superconductors we use in the LHC, which is more like a fabric. You can bend it, you can twist it. It's very forgiving, it's very nice for engineering and for industry productions. Niobium-3 tin is like a ceramic. It's not a ceramic, but it's very hard and brittle. So if you bend it or stress it too much, it will break, and the magnet will no longer work. So making a design which is robust enough that the magnet will survive all the training and all the operations is by far a trivial feat, and that took us a lot of time to develop this new magnet technology for the HiLumi-LHC, and this will be also a technology enabler for any future project.
But you're not changing the whole accelerator ring, you're only taking a part out. Is there a reason for that? Is there like the most important part?
Yeah, so this is the part that prepares the beams for the collision inside the detector. And yes, it's special in the sense that these are like focusing lenses in the telescope, where you want to adjust the lenses in a way that it makes the spot size of the beam at the collision point in the detector as small as possible to make the highest density and hence the highest rate of collisions in the detector.
So in the facility, in the building that we are here right now, it's a test bed of all the superconducting magnets that went already in the LHC, and now we are testing all the magnets that will go into the HiLumi. So all the infrastructures have been updated, and we are constructing a test bed to build approximately 1/4 of the magnet systems of HiLumi. We are building a complex, testing all the systems together. It will be the first time that we put things together, and you are making sure that when things are working together, nothing is fading, and you are pretty sure of that the HiLumi will be a successful project and it will deliver its physics targets. Approximately a decade ago, 9 to 10 years ago, that we already started prototyping, building small prototypes of the systems, and in the time of 2026, the machine will be stopped, the LHC will be stopped, and it will sleep for around 3.5 years. We remove the old LHC systems in the parts that are impacted by HiLumi. Not all the 27 kilometers, but around 1 kilometer of machine will be removed, and the HiLumi systems will be installed. And we are speaking about a timeline to see beam again around 2030, where we have the HiLumi beam circulating again, and physics production will start gradually from 2030 on.
You mentioned that there is a lot of energy being produced by obviously the particle accelerator. What are you doing with that energy, and how is being used beyond CERN?
So traditionally in accelerator complexes, most of the heat was just cooled away by cooling towers and then essentially just wasted to the environment or given to the environment without additional use. Now, in the recent years, the need for sustainability and for global thinking of your infrastructures has really taken a focus. So CERN is really trying to step up to that, reorient therefore the ambient heat cooling and all of that to communities in the neighborhood who will then benefit from distant heating of homes and apartment complexes. So this is all being implemented in parallel with HiLumi, part of the whole exercise to make our field more sustainable and globally integrated into the societies. I think what I would really like to illustrate or get across to the audience is that this is not a CERN project alone. We involved a lot of international laboratories and partners which are not permanent members of CERN, but which were really essential to the technology development. It's a truly international effort. Just to take a few examples, we have China, we have Russia, we had Russia, we have the USA, and we have Japan, deeply involved, and Canada, deeply involved in the production of the new technologies, even though they're not members of member states of CERN, but they're vital partners. So I think any future project in our field that we hope to realize after HiLumi-LHC will have to follow a similar path. It has to be designed really with a truly international collaboration.
More collisions and more energy are needed to understand even better what the LHC has discovered so far. And now, not even its waste heat is actually wasted. From mid-2026, the LHC will be on a long shutdown to get everything ready for its future. HiLumi.